Let's solve the following. Use the definitions of electric current and capacitance to show that C is equals to FR. So let's move on. So we know that capacitance is equals to Q over V, and we also know that I is equals to Q over T. So Q is equals to IT. So we have capacitance is equals to IT over V. So we need to remain with T here. V goes there. So you have V CV over I is equals to T. V over I is R. So T is equals to V over I is R. So T is equals to RC. But we all know that T is equals to 1 over F. That's period is equals to 1 over F. So substitute into the formula. So we are going to have 1 over F is equals to RC. So C is equals to 1 over FC, 1 over FR. So this is FR. So we've shown that C is equals to 1 over FR. Fig 1.1 shows a circuit used to investigate the properties of a capacitor. The capacitor is initially not charged, which means the capacitor is 0. When the switch was closed, the pointer of the ammeter was seen to deflect, but after 4 minutes there was no deflection at all. Explain this observation. So when the switch was closed, when it was closed, there was a deflection in the ammeter, but after 4 minutes there was no deflection. So we can see that when this switch was closed, there was a current which was moving here. The voltage across this resistor was the voltage across this battery. So when the switch was closed, the voltage across this resistor was the voltage across this battery, and since this was not charged in the first instant, this capacitor acted like a short circuit. So it acted like a short circuit. So you have your ammeter here and you have your resistor. So the capacitor acted like a short circuit. Since it's closed, switch is now closed. So yeah, so the capacitor acted like a short circuit. So in the second instance, after 4 minutes, so as the current is moving in this circuit, this capacitor is charging. So when it's charging, the voltage across the capacitor is increasing until the voltage across the capacitor is equal to the voltage across the battery, and the current stops moving. So the capacitor will now act like an open circuit. So this is a closed circuit. The capacitor will now behave like an open circuit. Once it's charged, the voltage across it will be equal to the voltage there, and it now behaves like an open circuit. So here the ammeter reads the first current, but when the capacitor is fully charged, there is no current flowing. The capacitor will act like an open circuit. So that will be your description. Right, sketch a graph to show the voltage across the resistor 100 key ohms. So let's sketch the diagram. Let's sketch the diagram. So the capacitor charges exponentially. Capacitor charges exponentially. So across the resistor, we are told to look at the voltage across the resistor. So the voltage across the resistor starts at 6 volts and it decreases exponentially until it reaches 0. So V, let's say V across the resistor is equals to V naught, which is 6 e to the power minus t over RC. So that will be the voltage across the resistor, and this is T in seconds, and this is the voltage in volts. So that's going to be the diagram. Last question. Calculate the value of current which flows in the circuit at the instant of closing the switch. So at the instant of closing the switch, let's calculate the current. So current I is equals to V over R, which is going to be equal to 6 divided by 100 times 10 to the power 3. It's a 100 k ohm resistor. So this is equal to 6.0 times 10 to the power minus 3, which is equals to 60 ohms. That's the initial current.